ready to go for the next session, and that so ma'am has already gone to that extent. So ma'am has enumerated various activation functions and loss function. So go through the discussion. So next topic is being covered by Dr. Surendra Hans. He is an assistant professor in the Department of Electrical Engineering, MNIT Jaipur itself. He has done his PhD from IIT Roorkee. So he's having interest in machine learning, deep learning, and also he's associated with Raman Lab. So and there are various research projects and research topics that are being covered through that lab. So sir, without taking much time, we may start, sir.
Yes, sir. Hello, sir. Good evening.
Good evening, sir.
So, is my voice audible and the screen is visible to you?
The screen is, yes, sir, it is visible.
Okay, okay. It's a completely black background is there. Is it visible?
Yes, yes, sir. Yes,
Okay.
yes, sir. It
Okay.
is.
So, thank you, sir. Let's start the session. So now
Yes, sir.
the session that is based on the activation function. So first, the benefit of the activation function. So the point is the activation function is used to capture this activation function is used to capture the non-linear pattern, capture the non-linear pattern from the given data, from the given data. Okay, so it captures the non-linear pattern. So if we will not apply the activation function, then our network or model does not capture the non-linear. Okay, so the network that will capture non-linearity, otherwise linear data, otherwise only real. So let me explain some example. So let this kind data set is linear data. So data set is without use of okay, so without use of activation function, we do the classification like this. Okay, and with use of activation function, so now so this rows that belongs to class 1, okay, and this circle that belongs to class 0. So this one, this that we are getting after the use of the activation function. Okay, this one is after use of activation function, and without use of activation function, this one is a without use of activation function. So here the output that we can write in a mathematical form. So let's say this one is the input layer. Okay, this one is the number of node in the first hidden layer. It's the number of node in the second hidden layer, and this one is the, let's say this one is the output. Okay, let's say this one is the input. This one is the hidden layer. Okay, and this first hidden layer. This one is the second hidden layer. Okay, so now the output or the expression that we can write. So W1 that is this one is a W1. Okay, this one is a W2. These are the weight. W3, these are the weight. Okay, so we need to connect each node of the input layer to each node of this first hidden layer. So now W1 transpose, okay, X is the kind of the input data that we are having this side plus this V1, correct? And that is the this sigma, that is the activation function. Again, that is a W2 transpose plus B2, okay. Then sigma, let's say this one is a sigma 1, this one is a sigma 2. Again, this W3 transpose plus beta 3, and this one again, that is a sigma 3. So this will be our output of this kind of neural network. Okay, where the sigma 1, sigma 2, and sigma 3, these are the kind of activation functions. So that I will discuss in detail the type of the activation function. Okay, so this is kind of sort of representation of the output, where this B1, B2, B3, these we call as a bias, and X, that is the input, and this one's the kind of the representation of the neural net. Okay, now the next one is uh, the next. So now ideal transfer function. So first let me explain the characteristics of the ideal, sorry, not transfer function, the activation. So what should be the characteristics of ideal activation function? Okay, so the first, the characteristics of the activation function that should be non-linear. So the first, the characteristic, it should be the activation function that should be non-linear. Okay, so if the activation function is non-linear, then it can easily capture the non-linearity from the data set. Now the second characteristic, it should be differentiable. It should be differentiable because we will use the gradient descent, which further use the derivative or differentiation to update the weights. Okay, so this one is mandatory. It should be differentiable. So now third one is, that is activation function that uh, should be computationally inexpensive. Computational is inexpensive. Inexpensive means it should be simple, okay, easy and fast. Okay, otherwise training that otherwise the training that will be slow. Okay, so now the fourth one is, it should be zero center. It should be zero center, or you can say it should be normalized. Okay, so like 10 hyperbolic, 10h. Okay, so here the mean that we will discuss in detail. So that is mean is equal to 0. Okay, so the mean that is equal to 0 here. This is the zero center. So that is the reason that this activation function that converges very faster as compared to other activation function. So convergence is fast. Okay, and the last one, it should be non-saturated. should be non-saturated. Okay, so non-saturating, let me just give an example here. Which side? Okay, non-saturating like sigmoid. Okay, sigmoid. So let me write here that is sigmoid, that I will explain through the transfer function, through the mathematical representation of the sigmoid. So sigmoid, that is in between 0 to 1. Okay, tan h, that is in between -1 to 1. Okay, so the point is, if the activation function is uh, saturate, okay, uh, on the high value, of the this input, so in this, the vanishing gradient, that problem that arises. So the vanishing gradient. So this vanishing gradient, that already that madam has explained, this vanishing gradient. The point is, when we do the back propagation, the gradient that will be very small. That is, let's say 0.1. Okay, then 0.01, 0.0001 means weights are not updating. The weights are not updating. Okay, so these are 5 characteristics that my activation that should have. Okay, so now let us explain now the first this activation function, that is a sigmoid. So I will explain this in detail, the sigmoid activation function. Sigmoid activation function. So sigmoid activation function. So this one is the graphical representation. This one is a x, sigma of x, and this one is a 1, and 0.5. So 0, this one is a 1, this one is a 0. Correct. So now sigma of x, that I can write an expression 1 plus e to the power minus x. Correct. So now the advantage of this sigmoid function. The first advantage is output that is in between 0 to 1. Okay, so output is in between 0 to 1. So this, just because of this output that is in between 0 to 1, we can use in probability. Especially we use in the binary classification. Okay, binary classification. So if the probability is greater than 0.5, the class that will belong to the class 1. If the probability is less than 0.5, the class or the data set that belongs to class 0. Like, okay. So that is the first advantage. Now the second advantage means it is a non-linear activation function because of this exponential. So it can capture the non-linearity, okay, that present in the data. So that is second, it's a non-linear. So just because of the exponential. So non-linear, just because of the exponential. Okay. Now the third advantage is it's a differentiable. It's a smooth function, so we can use in back propagation. So it's a differentiable. It is a differentiable function. Differentiable. Okay, and we can use this in a back propagation. Clear? So these are the few advantage. Now the disadvantage. Now come to the disadvantage side. So now the disadvantage of sigmoid activation function. So the first disadvantage is saturating function. It's a saturating function. So if you give the input value in between -infinity to +infinity, this one is a -infinity to +infinity. So I'm talking about the value of x. So if you give the input value in between minus infinity to plus infinity, zero. So now saturate zero. Saturate function. Okay, it's the output in between 0 to in 0. So saturate 0. Direct. So vanishing. Okay. Ma'am that also explain this vanishing gradient. So let's say W, that is a weight. So that is W nu is equal to W old minus eta, that is dou L by dou W. That is a partial differentiation of this loss function with respect to the weight. Okay. So if this gradient, if this dou L by dou W, if this is 0, so no update that will take place, meaning no training that will be done. So in that case, if this one is equal to 0, where this eta is the learning rate, okay, so now in this case, the W nu that will be equal to W old. Okay, so let us say that X is very large, that X, okay, this input, this so I'm talking about this X. So that is X is very large, then differentiation that is close to 0. Okay, and differentiation that is close to 0. So let me just draw a kind of graph representation of differentiation of not yes. So this one is a sigma dash. Okay, so now the point is, if we have the very high value of this x, then the differentiation that will be close to 0. So that is the main reason that hardly we use this sigmoid in the hidden layer. Okay, let me write this point here. So hardly we use this sigmoid in hidden layer. Okay, so we use this activation function, that is sigmoid, only at the output for binary classification. Okay, so that we use only at the output for binary classification. Clear? So here, this you can see here this uh, this this. So slope is 0 at higher value here. That is slope. Slope means that is a rate of change, that is a gradient, that is slope is 0 at higher value. Similarly here, the slope that is 0 at this high value means it's a negative, isn't it? Okay, so that is the first disadvantage. Now second disadvantage. So second disadvantage is non-zero center. This one is non-zero center. So non-zero center means after this applying this activation function in the layer, okay, is hidden layer. Let's say this one is a hidden layer. So after applying the activation function, okay, means the non-zero centered means they are not normalized. Okay, means they are not normalized. So either they all are positive or might be all negative. Okay, clear? So just because it is not zero centered, so consequence of this, the trading that will be slow. Okay, because it is not zero centered, the training that will be slow. So now I'm going to explain the reason behind this, how this training that will be slow if the activation function is not zero centered. Is it? So see, uh, let's say this one is a, so many layers are there. Okay, this like this. Okay, this one is the predicted this output. Okay, and this one is a, let's say A21. This one is a A22. Okay, and this is a W21, W22. Okay, and this one is a Y. Correct. So the value that is after applying the activation function, that is Y cap. Okay, and this one is the many layers are there. So here it is many layers are there. Correct. So now the L, that is the loss function, that is a function of this Y cap, and this Y cap, that is a function of Z. Okay. So now Z that will be, so here I am writing this Z that will be like this A means Z that is again that is a function of A21, that is a function of W21, that is a function of W22, that is a function of A22. Okay, clear? And it's a function of, that is a bias B31. Clear? And this Y cap, that is a sigmoid of this Z Y cap. Okay, so now this Z is, that is A21 W21 plus A22 W22 plus B31. Clear? And what about this dou L by dou W21? So this, as I said, this L, that is a function of this Y cap. Further, this Y cap, that is a function of this Z. Then Z is a function of this A21, W21, and so on. So now dou L by dou W21, that is, I can write this dou L by Y cap. Okay, dou Y cap divided by dou Z. Okay, so this Z and this Z, that is same. Let me just write here this Z capital, this Z. Okay, and dou Z by dou W2. Suppose this Z, that is a function of this. Clear? And what about this dou L by dou W22 is equal to dou L by dou Y cap? Can I write like this one? So dou Y cap divided by dou Z, and dou Z divided by dou W2. So now you see here this term, okay, and this one, that remains the same here. This one is the same. Okay, and now this dou Z by dou W21, because Z is this one, so now this will be equal to A21, and this will be equal to A22. Okay, so now A21 and A22, this one is A21 and A22 are the output of the sigmoid function. Okay, the output of the sigmoid function. So and the value that lie in between 0 to, the value of this A21 and A22, that is lie in between 0 to. So that is both are positive. Okay, lie in between 0 to, so both are positive. So now let us assume this common term, this common term that is negative. Let us assume. Okay. So just this A21 and A22, that both are positive, and let us assume this common term, this dou L by dou Y cap and dou Y cap to dou Z. This, let us assume this one is a negative. Okay. Then the both the gradient that will be negative. This one also and this one also. Okay. So if this common term, if this common term is positive, then both the gradient that will be positive. Clear? So that depends upon the this common term. So if this common term is positive, okay, then the gradient that will be positive, okay. And if this common term that is negative, then the gradient that will be negative, just because of this common term. So now we need to manipulate the weight so that we can minimize the loss function. Okay, this weight I am just talking about this W21 and W22. Okay, so in this process, so we can put the derivative either all positive or all negative, means that the changes that can happen either in a positive way or negative way, just because of this common term. Okay, so basically that is this gradient that is restrict, okay, in a single way direction, that is restrict in a one direction. So let's say, for example, I want to go from Delhi to Jaipur. Okay, but I cannot take left turn. Okay, the point is, the constraint is I cannot take the left turn. So in this way, it will take more time. Okay, so hello, I'm audible to all of you.
Yes, sir, you are audible.
Okay,
Sometimes some glitches are there, but you are
okay,
audible.
okay, okay. Thank you, sir. Thank you. So I cannot see the chat box, chat message. So the question or the doubt that I will take over at the last of this session. Okay. So now, so the example that we can understand this non-zero center. So let us say, so here on the way of this from this Delhi to Jaipur, so I cannot take, let's say, the left turn or the right turn. So it will take more time. Okay, just because of the constraint, just because of the restriction, means we can only move in this direction, because I cannot take the left turn. Okay, so that is the reason that training time that will be slow. I hope through this example the meaning of this training time that will be slow if the activation function is non-zero centered. I hope it is clear to all of you. Okay, okay, fine. So now that is the second disadvantage. Now the third disadvantage is, that is sigma of x is equal to 1 upon 1 plus e to the power minus x. Okay, so now computationally this activation function is expensive. Okay, just because of the exponent. So it take more time to compute. So now it take more time to compute. The reason is this exponent. Okay, so computationally it is expensive. So these three are the drawback, and three are the advantage of the sigmoid function. So I hope this sigmoid function is clear to all of you. So now second activation function is, that is tan h, tan hyperbolic, the hyperbolic function. Okay, so now the representation of this tan hyperbolic is f of x is equal to, that is e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. Okay, and the representation in terms of the graph. So this one is a x and this type of. So this one is a -1, this one is a plus. This is f of x. Clear? And this one is the differentiation of this tan hyperbolic. This one is a tan hyperbolic differentiation, this f of dash x. So f of dash x, that is equal to 1 minus tan hyperbolic, that is square, that is x. Okay. So now the advantage of this activation function. So this the second form of representation. So I can write, so 2 divided by 1 plus e to the power minus 2x minus 1. Okay, that's it's very simple way to represent in this form also. And take the e to the power x common and likewise. Okay, you have to set the equation so that we will get in the form of 2 divided by 1 plus e to the power minus 2x minus 1. So advantage, that is first advantage is that is non-linear, just because of this exponent. Okay. Second advantage is differentiable. And the third one is a zero set. This is the advantage. Okay, although this one is centered, that is the disadvantage in the sigmoid activation function. So now here it becomes the advantage. So now zero set. Okay, so here some gradients that are positive and some gradients are negative. So training time is faster. Earlier, the training time that was slow in the case of the sigmoid. Okay, now the training is faster compared to the sigmoid. Because some of the gradient here you can just connect with this point. Now the gradient, this gradient. So some of the gradient that are positive and some of the gradient that may be negative. Okay. So there is a no constraint. So that from Delhi to Jaipur. So in that one, that I cannot take a left turn, or let's say I cannot take a right turn, so that it will take more time to reach Jaipur. Okay. So here the zero center this tan hyperbolic. Okay, so that is the advantage. Now, so come to the disadvantage side. So now disadvantage. So first disadvantage, that is saturating activation signal. So it saturate the high value of the input x. So saturating activation. So just because of this, the problem that occur, that is vanishing gradient. Okay, so vanishing gradient. Second problem is that is computationally, that is expensive. Okay, so that is lesser than the sigmoid. So let me write here, that is computationally expensive, but lesser than the sigmoid. Why? Because it has more slope. So that is why this tan hyperbolic is used in place of sigma, in place of sigma. Okay, but this uh, sigmoid that we use on the this at the output side. Okay, as the probability that is in between, that is output that is in between 0 to 1, that is we use this kind of advantage uh, for the binary classification. Okay, so I hope this 10 hyperbolic that is clear to you, that is advantage and disadvantage. So training time is faster just because of the zero center, and this is a vanishing gradient, that is a saturating just because of the saturating activation function, and computationally that is expensive. But this 10 hyperbolic that we can use in a hidden way. Okay. So now the third, this one is activation function is more important, that is a ReLU. So nowadays we see now recent the model that use the this ReLU activation. So now the ReLU activation function, the representation is like this. So that is f of x is equal to, that is max 0 comma x. This is x. This is f of. Okay. So now the full form of this ReLU is rectified linear unit. One is a rectified linear unit. So that is the best choice in the hidden field. The best choice in hidden field. Okay. So now come to the advantage part, advantage side. So this one is the non-linear. Okay. Now second is non-saturated, is very important. So non-saturated. Okay. And the third one is non-saturated in the positive region. There is a negative region that is 0. So non-saturated in the positive region. Okay. So I should write here in the positive region. And it is computationally inexpensive because non-exponential, just because of the non-exponential. So it is computationally inexpensive. And the fourth one is the convergence. So convergence is faster compared to this sigmoid and 10H, compared to sigmoid and 10H. Correct? So now come to the disadvantage side. So the biggest disadvantage is it is not completely differentiable. So at x is equal to 0, it's a non-differentiable. So non-differentiable. Non-differentiable. So x greater than 0, that is 1. Okay, or that you can say this x, and x that is less than equal to 0, that is 0. Okay, and the second disadvantage is non-zero center. Okay, so we use the batch normalization. So normalize the this out. So it's a non-zero center. Correct. So non-zero center. So now the most important point is there is a one problem is dying ReLU problem. Dying ReLU problem. Okay. So first let us understand this dying ReLU problem. This is very important one. So the dying ReLU problem is means that is output of the activation function sometimes become equal to 0. Output of this activation function sometimes becomes 0. So whenever we apply the input, so the output of the activation function that is equal to 0. So that we call as a dead neuron. That we call as a dead neuron. So the dead neuron that remain forever in the dead region. Okay. So if suppose more than 50% of neurons, more than 50% of the neurons are dead, okay, a dead neuron, then we cannot extract the feature from the data. We cannot extract the feature from the data. Correct? So the point is, the question is why? Why it occurs? Okay. Then how do we solve this issue? Clear? So that is very important point. So let us understand this dying review problem. So let's say this one is the input x1, this one is another input that is x2, and w1, w2 that is a weight. Okay, and this one that is the output of this neuron, let us say that is a1. Okay, where a1 is equal to max of 0 comma z1. Okay, and where z1 is w1 x1 plus में w2 x2 plus में b1. b1 that is a bias. Correct? And let's assume this is an assumption. This one is an assumption. So let's assume this z1 is less than 0. Okay, clear? So this one is an assumption. This one is an assumption. Z1 that is less than 0. And here this one is a, let's say W3, and this one is a V2 that is a bias, and this one is a Y cat. Okay, fine. So this A1, because Z1 that is less than 0, so now A1 that will be 0. Yes or no? So that A1 will be 0. Then derivative of A1 with respect to Z1 that is equal to 0. Derivative of A1, that we will use this equality, okay, in the next this gradient. So thereafter this W1 and W2 that would never update, because this dou A1 by dou Z1 that is equal to 0. Correct? So now W1 is, that is W1 is W1 minus में eta of dou L by dou W1, and W2 you can say W1 new is equal to W1 old. Okay, so W2 new is equal to W2 old minus eta dou L by dou W2. Okay, so when we calculate this dou L by dou W1 and dou L by dou W, so in this ongoing process, we use this one dou A1 by dou Z1. So if this dou A1 by dou Z1 that is equal to 0, then this dou L by dou W1 and this dou L by dou W2 that is 0. Then W old is equal to W new. So that is B1, is a dead neuron. So sorry, not B1, that is B, that is, so this one is a dead neuron. Yes or no? Clear? So let us understand this dou L by dou W1, that is how it is equal to 0. So now let me write here. Okay, so let me write here this dou L by dou W1. So dou L by y cap, because L, that is a loss function, that is a function of this y cap, and dou y cap, that is by A1, and A1 by this Z1, and this Z1 divided by W1. Yes or no? Because this L, that is a function of this y cap. Okay, y cap, that is a function of this A1. Okay, so this L, that is a y cap, that it depends on this y, that is W3. Okay, this B2, and that is the output of this neuron. Okay, so output of this neuron, that is this A1. So A1, that depends on the this A1 that depends on the Z1, and Z1 that depends on the further. Let me write here, that is A1 depends on Z1, and this Z1 that is further, that depends on the W1, W2, X1, X2, and B1. So dou L by dou W1. Okay. So now you see this dou A1 by dou Z1, just because of this, that is equal to 0. And likewise, let me write here, dou L by dou W2 is equal to dou L by dou Y cap into Y cap divided by A1 into my A1 divided by 1, and Z1 divided by W2. Okay, so this one, so this will be equal to 0. So if this equal to 0, then this gradient, that is dou L by dou W1, dou L by dou W1, and dou L by dou W2, so this will be equal to 0. Okay, so if this weighted sum, okay, if this weighted sum, that is 0, then the derivative of this value, that is become equal to 0. Okay, so clear. So now question is how this W1 X1 plus W2 X2 plus B1, that is less than 0, how this Z1, that is less than 0. Okay, this one is an assumption. This one is an assumption, that is Z1, that is less than 0. So there is a first reason for this Z1, that is less than 0. That is the first reason. If Z1 is equal to 0, so dou L by dou W1, that is equal to 0. Dou L by dou W2, that is equal to 0. Okay, means that is a dead neuron. Correct? So now the point is, the first reason is that maybe the learning rate is very high, this eta. Okay, so W1 is equal to W1 minus my eta dou L by dou W1. So if learning rate is very high, so this will become very high. Okay, due to this eta, due to the learning rate. So now W new, okay, so W1 new, this one is the old, so that will be negative. So W1 new, that will be negative. Correct? So in the next cycle, so W new, that is equal to W1. Okay, so next cycle, W1 new is equal to W1. So W1 X1 plus my W2 X2 plus my B1, that is less than 0, because this one is negative and this one will be less than 0. So that is the first reason. Clear? Now the second reason that may be high negative bias. So that is B1, that is B1 that is less than 0. So now W1 x1 plus my W2 x2 that is less than B. Correct? So the reason that may be that initially that you have started with high negative value of B1. Okay. So second reason is you are also updating your bias value with this same updating rule. So B1 is equal to B1 minus may eta of dou L by dou B1. So eta is very high, then B1 that may be the negative. If eta is very high, then B1 that is very maybe the negative. If B1 that is very high, that is negative value, so that may be the chance of this Z1 that is less than 0. Yes or no? So now the solution is first set the learning rate that as low as possible. Let's set the learning rate as low as possible. Okay. The second, that set the bias that is positive value, that best value is bias that is for 0.01. And third one that is don't use rate. So just you keep the advantage of ReLU function as such. Okay, in the next variant. So next variant is leaky ReLU. Then parametric ReLU. Okay, so this one is a linear variant. These two are, that is a linear variant. So linear transformation on ReLU, that is a linear variant of the ReLU. Non-linear variant, so that is ELU, that is exponential linear unit. Okay, so we apply the nonlinear transformation this on ReLU, that is ELU, that is exponential linear unit, and that is SELU, that is SELU, that is scaled exponential linear unit. Okay, so now the leaky ReLU. So the time is 7 o'clock. So there's many things to train leaky ReLU parametric. Okay, so now the leaky ReLU. This one is the leaky ReLU. F X. Okay, so the leaky ReLU. This one is the leaky ReLU, and this one is the this f of x, that is here, that is f of x is equal to x, and here f of x is 0.1x. That is a leaky ReLU. 0.1x or that is 0.01x. So that is f of x is equal to, that is maximum of 0.1x, comma x. Okay, if x is greater than equal to 0, that is x less than 0, that is 0.01 of x, that is fraction of x. So benefit is when x is negative, the derivative that will not be equal to 0. So the advantage is when x is negative, the derivative that will not be equal to 0. Okay, and the second advantage is non-saturated. Okay. So both unbounded. It can extend it in either direction, in positive direction or negative direction as well. Clear? So now the next one is that is easily we can compute this leaky rate just because of the known exponential. It is that we compute it because of the known exponential. Known time Rayleigh problem. Known time Rayleigh problem. Okay, and this close to 0 cent. Close to 0 cent. So non-saturated. Okay, and the Z when x is negative, that is derivative that is not equal to 0. Okay, so now question is why this 0.1? Okay, this is 0. Why this 0.01? Why I took this 0.01? So answer is we can change this in parametric value. Okay, so now in parametric value, that is f of x is equal to that is x if x is greater than 0 and a of x otherwise. Okay, so now this is f of x is equal to x, and here this one is f of x is equal to that is ax, where a is the trainable parameter depending on the data. So that's the hyperparameter. You can take this value is a 0.01, or you can take this value is a 0.02 or 0.1, or up to the application. Okay, correct. So that is one is the second one is a parametric value. Now third one is the ELU. Okay, so ELU that is x if x is greater than 0, and that is alpha e to the power x minus 1 if x is less than 0. Okay, where alpha that is constant. So generally the value of this alpha that in between 0.1 to 0.3 generally, correct, and the differentiation of this ELU is equal to that is 1 if x is greater than 0, and this ELU of x plus may alpha that is if x less than equal to 0. Correct. So that is this one is always this continuous and differential. Always this one is a continuous and differential. And the advantage is that is close to 0 center. Okay, so just because of the 0 center, the convergence is faster. And this experimentally that it is proved that the result is much better than the on the test data. Okay, so the next advantage is does not have the dying Rayleigh problem, and this is always continuous as well as this is the differentiation. Okay, now disadvantage is that is a computationally that is expensive. Okay, because of this exponential term. So since it is a 0 center, so convergence is fast. So now the fourth one is that is SELU, scaled exponential linear unit. So scaled exponential linear unit that is lambda, that is x is greater than 0, so alpha e to the power x minus alpha is x less than 0. Okay, so here that is alpha and this lambda. Okay, so these are the fixed parameter, not trainable parameter. Now you remember this point, this alpha and this lambda is the fixed parameter. So there's a certain value. Okay, so now I don't know right now the exact value of this alpha and lambda, but this one is the fixed parameter, so it's not trainable. Okay, and the differentiation of this SELU is lambda, that is 1 for x greater than 0, and alpha e to the power x for x less than equal to 0. Okay, so this is the kind of the say loop, and the last one, that is the softmax. Okay, so in softmax that we use for the multi-class classification, correct? So multi-class classification, let's say the output of the final layer is 0. Let's say 1. Let me in the next page. So let's say the output of the final layer is 1.3, this 5.1, this 2.2, and this 0.7, 1.1 likewise. Okay, this one is, that is x1, this one is for x2, x3, and x4, and x5. Okay, so softmax, that is representation of the softmax, is e to the power x1 divided by sum of e to the power x5. That is the representation. So now this one x1 that will be replaced by e to the power x1 divided by e to the power x1 plus e to the power x2 plus e to the power x3 plus e to the power x4 plus e to the power x5, and x2 that is replaced by e to the power, this one e to the power x2 divided by the same common term, x3 that is e to the power x3 divided by the same, this one is e to the power x4 divided by same. Okay, so all these quantities that will lie between 0 to 1, and if we add all these, then it is sum up equal to 1. Okay, so softmax, so let's say this one is 0.02, 0.90, so 0.05, 0. Let's say 0.1 and 0.02. Okay, so this one is a 2% probability that it belongs to class 1. It's a 90% probability that it belongs to class of, let's say, dog. This one is a 5% probability that it belongs to class, let's say, cat. Okay, so here that we are not confident after seeing these two numbers that uh, that cat or dog proportional, this probability is high, but softmax, okay, does uh, this in a better way. Okay, so there is a 90% chance of dog is having in a image. So softmax that does not directly discard the lower probability. That is the point. Correct. Now the disadvantage is, so now disadvantage is it is computationally expensive because of the multiple exponential dysfunction. Multiple exponential. Okay. Now the last one, that is a swish. So that is y of x is equal to x of sigmoid of x. Okay. So now the representation of this sigmoid, swish is like this one. So it is not bounded in between 0 to 1. Okay, so this one, that solve the vanishing gradient. Okay, so that when a switch, okay, and so far that we had discussed the 6 activation function. Okay, and let me explain this definition one more time, just to capture the nonlinear pattern from the given data. So I hope this all activation function that is uh, clear to all of you. If you have any doubt, then please let me know. Stop sharing. Oh, what do we? Yes. Is there any doubt? Okay, so that's all from my side. So that's
Participants have no doubt, then maybe we can wind up the session.
so Ashutosh, is my voice not audible properly?
No,
It's
no,
audible.
it is audible. It is audible. So, participants, if you have any query, you may ask, sir, or else we may wind up for today. We will meet tomorrow at sharp 10. So, Nitan and ma'am will be taking the class, the lecture on optimization. She might also be going through some hands-on parallelly. So, if anyone is having some query, please feel free to ask. Anyone? So I think, sir, there is no query. Sir, please allow to log in two devices. So I think this kind of issue is not uh, related to our course. So definitely it will be handled by E and ICT only. Okay, we will refer to them if they allow. So it is due to security concern they are not allowing login into two devices. Anyway, uh, if you have any query related to the session, you may ask. Okay, sir, one query is there.
Yes, yes.
How ReLU handles non-linearity?
Okay, so see, this ReLU, actually the important point of this ReLU is that is this one is a non-linear nature. Okay, this one is a non-linear nature. So that I told you in the very beginning of this activation function. So the characteristics, this one, yes. So that the activation function that should be non-linear. So if the activation function is non-linear, then only it can capture the non-linear pattern from the given data set. Okay, so the point is how it captured the non-linear pattern, so that that already that ma'am has explained. That is through this activation function and this w1 x1 plus w2 x2. If we put this in a ReLU activation function, okay, then we can capture. If we don't use the this ReLU, okay, so this is the kind of this without use of the this activation function, and with use of the this after that use of the activation function. So the all the this activation function that are having the non-linear nature. So this one, there's a sigmoid that is a non-linear, that is again that is 10H, that is a non-linear. Now you see, okay, that ReLU, that again that is the softmax, okay, and this leaky ReLU, that every activation function that has a non-linear nature.
ध्यान से lecture चल रहा है
Okay, so I think that I have not shared the screen. Okay, I explained without sharing the screen, so sorry for that. Centered around the zero means symmetric around this is a 10 hyperbolic, that is centered around the zero. Okay, so P3 that is centered around zero means symmetric around the zero. Okay, so 10H, that is that you can call as a zero centered. The rest all are not zero centered. The leaky ReLU and this one, that is close to zero centered. So now is activation function that is also a hyperparameter? Yes, actually is not exactly, but there is some constraint that means means it is not kind of the fully that hyperparameter. There is a means if suppose you have some data set, then better to use the sigmoid, okay, softmax, then uh, this sigmoid just for binary classification, that softmax, that is multi-class classification. Okay, there's sigmoid that I told you that is never we use this sigmoid at the mid of the this neural network. Okay, so better to use the sigmoid at the output layer. So these are the some few points that we should know when we apply the activation function.
So, Preeti ma'am, I would also like to add more one point. So basically, the hyperparameter, we understand about what hyperparameter means. So since if you look it from a perspective of picking up one function, that may be treated as a hyperparameter. But once we have selected some of the any of the activation function, so the question is, are you going to tune the values of the function? So in the activation function, it is rarely there. So that's why, in some sense, we can say it is hyperparameter, but not in general. Means in concrete terms, it is all the about the function only. Activation function is a mathematical function. Once you have selected, you are not going to tune it anyway. Okay, you just provide the input and you just get the output. Okay, and you apply different threshold. So activation function, in very concrete term, we cannot say that it is a hyperparameter. So yes, centered around zero means symmetric around zero. Yes, it is all about the symmetricity only. Yes. So it was it was about to referring how the distributions are there and how we treat those distributions. So it's referring to, in some sense, it was asymmetric.
Yes, any other doubt? Okay, okay, thank you, Vikas sir. So let's wind up the session so that we will meet tomorrow at 10 o'clock.
Hello.
Hello, yes, sir.
No, there is no doubt, sir. Okay. So we are
Ah,
concluding the session,
yes,
sir. Uh, so thank you, participants. We are joining back tomorrow and winding up for today itself. So thank you all. We may leave the session.
okay. Thank you, Ashutosh.
Thank you, Astos. Thank you. Thank you, Surendra sir.
Yes, sir.
Thank you. Okay, take care.
Astos, you may end the session.
Okay, sir.